So we'll start off with the most obvious thing. You have looked at it probably a dozen times. I will still assume you haven't and look at it another time. So if you want to solve in a general constraint graph like the one around over here, which is say A, B, C, D, E, and F, and let's say I'll not write down, the domains are all R, G, and B. So we start off with a search where nothing is initialized. Absolutely nothing is initialized, and I apply backtracking. So the details of backtracking need not be told. Now, every branch will select any one variable and assign any value to it. So A is equal to R. That is, okay, why am I writing down? It's my state. The rest unassigned. If I don't write anything, it's unassigned. A is equal to G. A is equal to B. B is equal to R. B is equal to G, all the way and so on and so forth till F is equal to B. And then it's a backtracking. I'll select this one and I will add the second variable. Okay, A is R. B cannot be R because they share a constraint of uniqueness. So B can be G. B can be B. Remember, the first one is the variable, the second one is the value. Or I could select instead a C. C can be R, and so on and so forth. And if you look at it, so how many branches exist out at the first level? So the number of branches out at the first level is the number of variables. Select any variable and assign any values from the domain. N variables and D value of the domain. Here N is equal to A to F, 6, and D is 3. Here the only thing that happens is that I have A is equal to R assigned. I'm doing complexity analysis, so I say that I do not know how many constraints will become valid, how many values will now not be possible. So let us say no constraint got activated. So one variable is assigned. I have n minus 1 variables and it could take any one of the D values. None of the constraints work. Next level, it will be n minus 2D, all the way up to when I have just one variable which is there, which can take in D values. Complexity analysis, sum this up. D will get common, n minus 1, n minus 2, n minus 3, and so on and so forth. It becomes factorial n times D. And if you are assuming what did I do, why did I multiply it up and not sum that up? This is the child raised by one parent over here. The children raised by ND parents is this into ND. This is the child of one parent over here. All the children are n minus 2D times the number of children over here. This will be the number of children raised by one parent. The number of children will be the number of children over here. So it's a multiplication of all of these and not the sum of all of these. So it appears bad, and of course we will do what you have been doing and you already know, is to take the commutative property of this problem, which is A is equal to R, then B is equal to G, is same as B is equal to G and A is equal to R. The order just does not matter. It doesn't matter in which order do I solve it, as long as I am solving this little thing up. And that means I could do exactly what you are used to, and therefore I will just write it around that, let's say the order of variables is A, then B, then C, then D, then E, then F. You can choose whichever order that you like. There is no compulsion on what order do you need to go to, and therefore the same problem, I only have 3 options instead of 6 times 3, 18. A is equal to R, A is equal to G, A is equal to B. Backtracking, I only have B is equal to, I cannot select C, my order is fixed. First level A only, second level B only, and we can just take in 2 values. B is equal to G and B is equal to B. Third level is C only, and so on and so forth. So again, if I do, so first level just 1, second level they are D options, D values. The second level, they are D options. Here it's 2, which is D minus 1, but one constraint got activated. In general, I have less idea for a general graph how many constraints will get active. So it's D, it's D, it's D, and therefore it's D raised to power N, which is the backtracking solution. You've been doing it for so long, exponential complexity, you already know that. And that's my solution. So, the purpose of this exercise was, of course, not to repeat what we have already studied, but to use the same exciting term, which is a heuristic. So, could we add a heuristic to this solution? Previously, when I defined heuristic, I said it's something to do with the problem design. So the problem designer gives the heuristic to you. He explains you the problem and then you say there is a heuristic. So there was nothing like a heuristic for the A-star algorithm in general. There was nothing like that. For the traveling salesman problem, it was different. Water jug problem, it was different. Missionaries and cannibals, it was different. Going through a grid, it was different. So it's a part of the problem. However, here, we will make heuristic which will be valid for any constraint graph or which will be valid for any constraint satisfaction problem. So we'll quote in some generic heuristic. Now, what can I exploit in order to get the heuristics? There are 2 things that I can exploit in order to get heuristics. The first one is right over here. Who said this is the best order possible? Who said this is the best order possible? Why not first B, then A? Why not first D, then B, then F? Why not F first? Why not E first? So, how did I get this order? And therefore the heuristic will be to select which of the permutations gives the best, fastest results. Now, in fact, it could be generalized even further. Why only A at first level? Why not in the first branch, I will say B only. However, in this branch, I will say E only. So, could this permutation be different for different branches? Yes. Who said it's gonna be level by level? It could be, permutation could be different for every branch. Every branch could have a new permutation of selecting variables. So, how do I select variables is my first heuristic. My second heuristic is that who said I try B is equal to G first and then B is equal to B, that's best. Maybe the answer is the other way around. So, in which order do I process my values? That is a second heuristic that I'll have. Maybe if I select B is equal to B first, then I get a solution in this branch itself. However, if I try b is equal to g, I need to backtrack, which is bad. So the next few minutes are going to be designing such heuristics about which variable to select and which value to select. Now, I'm not giving in the pseudocode, of course, because it's been done multiple times. The generic structure looks obviously like this, that I have my backtracking recursive function, which, why recursive, why not BFS? Because I need to be memory efficient. I lose memory much before I lose out of anything else. This is my representation of the problem. These are the assignments which have already been made. And of course, I've got a list of unassigned variables, and I've got in the domains of all the variables. So all that I need to do at every step is that I need to select a variable by heuristic out of all the unassigned variable vars. Also, what I need to do is that I need to decide the order of values, say Z. Then I go to all the values for all values Z in Z, and I simply say that is Z consistent. So if Z is a consistent move, that means it does not break any constraints of the rule. And if Z in fact is what is consistent, then I just add the variable value. Assignment variable was V, value was Z, to my assignments. I recursively do a call. So if backtrack on the same problem, assignments, values, domains, that's variables, and I have all the assigned V, so I subtract that up. If I get a solution, then I simply return a success. And if I don't get a success, then I need to undo. So I remove V is equal to Z to assigns, and I'll try something else. I'll try some other values. And of course, if finally nothing happens, then I return that, oh my God, it's not possible. I return a false. And that is exactly where the heuristics are coming into play. How do I decide my own variables? So that's one. And how do I order in values? That's where I'll use in heuristics. And of course, I do say that if my variable list is empty, there are no more variables to assign, then I return a success that, hey, I got a solution. So that's an old backtracking code. You've looked at it probably around a dozen times, and the only reason of pointing out probably another time out of a dozen times is to say that these are the two things that we would be changing around over here, or that's where now we will be deciding based on some kind of a heuristic. So let's get to the heuristics. And in order to get to the heuristics, I take in exactly the same constraint graph, let us say here, and I try to solve this constraint graph, and using a same backtracking algorithm, I'll see if I can do something which is more intelligent. So I'll get rid of this because you already know this, and that'll give me a little bit more space. And what I'll do is, above every variable, I will write down its domain. So it's RGB, 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 and RGB. If I have an assignment, I'll write it down on the side is